In this video, we're going to go ahead and cover section 6.4, vectors and dot products. This is also part of unit 6, additional topics in trigonometry. You'll be happy to know that there's, those of you who aren't too crazy about the trig, that there's not that much trig in this one. So there you go, okay? We have a definition here about the dot product of the vector u, which is given by the components u1 and u2, and the vector v, components v1, v2, is the following. U times v is equal to basically the first components times each other plus the second components times each other. In the previous section, we talked about addition and subtraction, so we're going to focus more on multiplication in this one. Okay, here's how you do it. We do have some properties we want to cover first before we go into the actual example. Let u, v, and w be vectors in the plane or in the space, and let c be just some numbers of scalar. Okay, we have that if we're multiplying u times v, this is the same thing as multiplying v times u, so we can go kind of backwards. If we multiply the vector times 0, well, anything times 0 is still going to be 0 in vectors as well. We have the property here where if you're multiplying u times a sum of vectors, you can use the distributive property to give you u times v plus u times w, okay? And then we have the magnitude right here squared. So the magnitude squared is actually going to be equal to the vector times itself. And we're going to actually deal with this one a little bit backwards. You'll see what I mean in a bit. And then we finally have our scalar right here. C times the sum of u plus v is the same as c times, oh, actually this should be a multiplication. So this is a multiplication, not an addition sign. Okay. Just double check that real quick. Yeah, it should be multiplication. I'm not sure why I put a plus there, but anyway, c times u times v is the same as rearranging these. So we can say c times u and then times the vector v, or we can do the vector u by itself, then multiply this by the vector v, and then multiply it. The idea is to multiply the scalar times one of them, and then you can use that new vector to multiply times the other one and use the dot product that we did up here, or up here, okay? So let's just jump right into it. We have our example. Example number 1. It says find each dot product. For letter A, we have 3, 4, and 2, negative 3. So we're going to, let's let this one be U, and this one be V. Okay, by our definition, U times V, okay, is going to be equal to basically this guy. So 3, 4 times V, which is the other components right here, 2, negative 3. And we're just going to multiply V1 or U1. So this is like U1, this is V1, this is U2, V2. So the U1 and the V1 go together. Okay, wait, what I did there? Sorry, U1, U2 is what I meant to put here. And then V1, V2. I'm just all over the place this week, guys, I tell you. All right, so what we do is we take our first numbers. So we're going to do 3 times 2. So these two plus the second number. So 4 times negative 3. And this would give us U1, so U1 times V1 plus U2 plus V2. Okay, so these are both U's. It's kind of hard to see there. These are both V's. Yeah, you just, work it out. So we have 3 times 2 is positive 6. 4 times negative 3 is negative 12. And 6 minus 12 is equal to negative 6. So let me rewrite this because it's a little hard to see. I'm going to have to switch colors on that one. And that's it. That is the dot product of these two vectors. Okay, let's look at the next one. We have negative 3, 5, and 1, negative 8. So for this one, let's let this first one be equal to our u. So we'll put the u here, u, and this would be u1, u2. This is v, so this would be v1, v2. We're going to go right into the calculation for this one. Okay, so u times v, we're looking at negative 3, negative 5 times, let's do this one in blue, I guess, times, oh, that one doesn't work, so I guess we're sticking with black. So times 1, negative 8. Okay, so same thing as before, we take our first component, so negative 3 times 1 plus the second component, negative 5 times negative 8. Okay, negative 3 times 1 is negative 3. Negative 5 minus 8 is going to give us positive 40, so plus 40. And negative 3 plus 40 is just positive 37. And that is it, believe it or not. That's it for this first example. Okay, let's go ahead and move on to the next one. We have example number 2. I went ahead and spaced these out pretty spaced, so we have plenty of room. Okay, so you could probably fit all this on one page, maybe a page and a half, just giving the heads up. Find each quantity. We have let u equal to 3, 4, and v equal to negative 2, 6, and then we have three different things going on here. Okay, so let's look at letter A first. I'm going to go ahead and just kind of work this way. Well, I guess I can work down. We'll try it out. We'll try something. We're going to do u times v first. So that means I'm going to calculate this part first. I'm just going to kind of bring the v down with it. So u is 3, 4. So 3, 4 times v, which is negative 2, 6. And then this v, I'm just going to kind of put it here on the side. I'll deal with it after I finish these two, okay? So just like the problem before, we take our first components, so 3 times negative 2, and we're going to add that to 4 times 6. And I'm just going to kind of put this in parentheses here and bring that v down. Okay, so 3 times negative 2 is going to give us negative 6 plus 4 times 6 is 24. And again, I'm just bringing down my v here, my vector v. It's the one on the side. Negative 6 plus 24 is positive 18 times v. So you will notice at this point that these actually came out to just a number, a scalar, right? Which is we kind of had on the other side. So we're going to multiply this scalar times my vector v, which basically just changes I guess you could kind of say the length of it if you were to graph it, okay? So 18 times v is going to be 18 times my vector v, which is this guy. So negative 2, 6. And we just distribute at this point. So I should probably put equal signs everywhere. It's going to be 18 times negative 2 is going to give us negative 36. 18 times 6, let me see. That's like saying 3 times 36, which is 108. There you go. So yeah, and we have a brand new vector that you will notice is 18 times what it originally was. So if you think of it graphically, kind of a small vector here, this is a lot, a lot bigger. Okay, and that's it for letter A, believe it or not. Okay, let's look at letter B. Let's just kind of work here vertically. For letter B, we have u times u plus v. So we kind of have to go back to our previous unit here. And I think I'm going to do this part first because, well, it just seems easier to me. Okay, so I'm going to go ahead and add u plus v. I'm going to bring down my u with it. So u plus v says we're going to take positive 3, 4 plus negative 2, 6. So I'm taking this plus this, and I'm just going to bring down my u. And you could distribute. You could do u times u plus u times v, but like I said, I just think this is going to be the easier route. So let's see. When we're adding, we just take our components, we add them. So it's going to be like saying 3 plus negative 2, okay? And then 4 plus 6. So I'm just taking, again, not the x's, the I components, if you think of it in terms of I and j, and then putting them together, and then the second component and putting those together. And that's going to give us, let's see, 3 plus negative 2 is 1. And then 4 plus 6 is 10. Bring down our u, which is just kind of hanging out right here. And now we're going to replace the u with the vector that it represents, so 3, 4. So now I'm going to go ahead and do 3, 4, because that's what u is, times, so dot product 1, comma 10. And now this becomes just like what we did in the past where you're multiplying two vectors. So this is going to be 3 times 1 because we take our first ones and we multiply them, plus the second one, 4 times 10, which is 3 plus 40, okay? And 3 plus 40 is equal to 43. And you will notice at this point that we have a scalar, yeah? So it's no longer a vector. Interesting, interesting. Okay. All right. Last one for this example, we have letter C. And this is asking for the magnitude of V. Remember, that's what these symbols like kind of like a double absolute value, so to speak. Okay, but it's magnitude. So we want the magnitude of V. So on our page before, okay, just to kind of quickly show you, we have that the magnitude squared is equal to the dot product of V. So I kind of want you to add something here. If we want to go, I guess a little bit backwards, okay, let's say we want to do just the magnitude of V. Well, it's like getting rid of the square, right? So you just square root both sides. So this would be equal to the square root of the dot product of V, of the vector. Okay, so we can also write this like this if the occasion asks for it. Okay, so let's go ahead and let's do that. So this is going to be equal to the square root of V times V. Okay, so we're going to calculate V times V first. So we have the square root of my V is negative 2, 6. So negative 2 comma 6 2 times, because that's what that means, right? And this is going to give us the square root of, I take my two first components, so negative 2 times negative 2 plus the second one, so 6 times 6, okay? This can be rewritten as, and I'm just going to write it this way because you'll notice that when we do these, we can kind of skip to the step here. So negative 2 squared plus 6 squared. Does that look familiar to you? Okay, that's a plus, okay? So plus 6 squared, and then that gives us the square root of 4 plus 36, which is the square root of 40. But of course, we don't want to leave it like that. We want to make sure it's in a simplified radical form. So I know that 40 is the same as 4 times 10, and the square root of 4 is just 2, right? If you want to make that intermediate step, you could do this. Square root of 4 times square root of 10. This is just 2, so we're left with 2 times the square root of 10. And this represents the magnitude of this vector, okay? And that's it. That's it for this example. Man, I had a lot of room left. If you want, you can put example 3 underneath. I'm going to go ahead and go to my example 3. Um, and we're almost done, guys. We only have, I think, 1 or 2 examples left. So really short video. The angle between two vectors. Okay, so now we're going to use a little bit of trig, nothing too crazy. We're going to use cosine. Okay, we have that if theta is the angle between two non-zero vectors u and v, then cosine of theta is equal to the dot product divided by the dot product of the magnitude of each of those vectors. So if all those words were a little bit much, I mean, just follow the formula, guys. Follow the formula. Plug everything in and work it out. We're going to go into an example. Find the angle between u equals vector with components 2, 1, and a vector v with components 1, 3. So what I'm going to do here kind of on the side is just kind of show you what this might look like. And we're not going to graph too much with this section, but I do want to show a few of them. So 2, 1, let's see, 1, 2, say 1 is right there. So 2, 1. So 2, 1 is about right here. So we have this vector right there, okay? And then this is vector u. I'm going to put the u right here. So vector u. And then v is 1, 3. So 1, 1, 2, 3, about right there. And this is v. So we want to find basically the angle between these. So this angle right here, that is what we're looking for. That's what we're doing with this problem, okay? So let's work it out. We have that cosine of theta is equal to the dot product of u and v. So these two right here, okay, so 2 and 1 times 1 and 3 all over the magnitude of u times the magnitude of v. So the magnitude of u is going to be this one. So I'm going to put that here inside my little magnitude lines. I don't really know what else to call them. Times the magnitude of v, which is 1 comma 3. Okay, so there's my formula with everything plugged in. So this formula with everything plugged in. Let's work it out now. We have, move this down just a little bit. We have that cosine of theta is equal to this part up here. We're just going to multiply. So 2 times 1, remember these two kind of go together, plus 1 times 3, those two kind of go together, all over the magnitude of this one times the magnitude of this one. So for this one, remember how we did the one before? It was just the square root of, and then it was this squared plus this squared. It's the same concept. So we're going to have the square root of 2 squared plus 1 squared, right? So we kind of have this whole thing here times, well, the same thing for this one. So square root of 1 squared plus 3 squared. And if you're not sure where these are coming from, remember that this is just the same as the square root of v times v. In this case, this is the vector times itself, so I'm just going to use that one. It would be like saying 2 times 2 plus 1 times 1 for this one, which is the same as 2 squared and 1 squared. So that's where this is coming from right here, and it's the same concept with this one. Okay, so let's go ahead and work that out. We have 2 times 1 is 2, 1 times 3 is 3, so 2 plus 3, all over the square root of 2 squared is 4 plus 1. Okay, so we have 4 plus 1 for this one, times, I'll put this in parentheses, this one's going to be the square root of 1 squared is 1, 3 squared is 9. Okay, and I'm using the room because I have a lot of room on this page, so why not? Um, let's continue. We have 2 plus 3 is 5. And then 4 plus 1 is going to be the square root of 5 times 1 plus 9 is going to be 10, so the square root of 10. So we have this kind of like weird looking thing here. So cosine of theta is equal to this 5 over the square root of 5 times the square root of 10. And at this point, we're basically just going to use a calculator. So I'm going to go ahead and combine these bottom ones to the following 5 over the square root of 50. Because again, I'm just going to plug this in at this point. We want to find theta. So of course, to find theta, we're going to have to use the inverse. Remember, the inverse is always used to find the angle. So if I do the inverse of this side and the inverse of this side, I get that theta is equal to arc cosine of 5 over the square root of 50. Or if you prefer the other notation, you can also do the inverse of cosine like this. It's the same exact thing. Okay, so let me do that very quickly on my phone, and I will show you what it looks like. Okay, so here it is. Oh, not that. So let's rewind that. Okay, so we have our calculator here. Remember to change this into degrees because we are looking for the degree version of this. It's kind of bright, sorry about that. Here we're going to go ahead and type in what we're looking for. So the inverse of cosine, and then 5 divided by the square root of 50, and there it is. The answer is 45. So it looks like the angle between these two is just 45 degrees. Okay, and that's it for that one. Okay, so let's move on to the last. I think there's one more example. Yes, one more example. And this is the last one we're going to go over. There is a little bit more in this subunit, but I think we're only going to go over it if we have time because we do have kind of a busy week this week with the notes. So we'll kind of play it by ear. We have the definition of orthogonal vectors, kind of a weird word, orthogonal. The vectors u and v are orthogonal or perpendicular if and only if, that's what this means, u times v equals 0. So if the dot product is equal to 0, that means that the two vectors are going to form a right angle of sorts. So right angle, remember, it's equal to 90 degrees. I'm trying to do this, I can't hear with my pens, but it'll be something like that. Okay, so often the vectors are like, slanted. You want to see if this forms a 90-degree angle. You use this to check. Okay, so let's go ahead and do example 4, which is the last one. Determine whether the vectors u, 610, and v, negative 1/3, 1/5, are orthogonal. And I like this one because it has fractions, and I know that we just love fractions in this class. So let's go ahead and I'm going to graph these first just so we can kind of see what they look like, and then we'll solve it. So let's do the graph over here. And we do have some fractions, so it's going to be a little bit of, estimating here. 6, 10. So 1, 2, 3, 4, 5, 6. There's 6. The one's going to be really close because of that negative. And then 10. I'm just going to, let's see. We'll go by twos. 2, 4, 6, 8, 10. There we go. That's 2. All right. So 6, 10 is going to be over here somewhere, which means this first vector does something like that. That's at 6, 10. And then we have this really small vector, negative 1/3 and 1/5. So I probably should have made this a little bit bigger, but it's like super tiny right here somewhere. Well, you get the idea. It's somewhere right here. So our question is this perpendicular? Is it orthogonal? Let's check. Let's plug it into our formula here and see if it comes out to 0. So we're going to do, let's see, u times v is going to equal to 610 times this one. So negative 1/3 and then 1/5. Okay, that's going to give us, we're going to do the first one, so 6 times negative 1/3 plus these two go together, so 10 times 1/5. 6 times a third is like saying negative 6/3. And then 10 times a fifth is like saying 10/5. Remember, you can just kind of put this over 1 and then multiply across. Okay, so negative 6 divided by 3 is negative 2. 10 divided by 5 is positive 2, and it does equal to 0. So what does that mean? That means that these two vectors are in fact orthogonal. So this means that u, trying to make it bold, u and v, so that means that these two vectors, okay, are orthogonal. And we're done. Okay, believe it or not, that is the end of these notes. As always, if you have any questions, please let me know.